A cargo ship weighs 85,000 tons and floats at sea level. The land ahead rises 85 feet above the ocean. No ramp exists that can lift that mass over a continent. Yet every day, vessels cross Panama without engine power, winches, or inclined planes. They enter a concrete chamber, doors close behind them, and 26 million gallons of water pour in from above. 8 minutes later, the ship floats at the summit. When the United States took control of the canal project in 1904, French equipment lay rusted in the jungle. Decades of tropical disease, landslides, and flooded excavations had defeated the earlier attempt to cut a sea-level trench across the isthmus. The French had believed that carving straight through at ocean level, the method used at Suez, would work in Panama. It did not. American engineers faced the same 40-mile corridor, the same mountains, and the same seasonal floods from the Chagres River. Chief Engineer John Stevens proposed a fundamentally different approach. Instead of carving down to sea level, build a dam to create an artificial lake 85 feet above the ocean, then lift ships to meet it. The solution inverted the problem. If the land was too high, raise the water higher. The decision required three components working in sequence. First, the Gatun Dam would impound the Chagres River to form Gatun Lake, a reservoir large enough to store the water volume needed for every ship transit. Second, a system of locks would function as water elevators, raising vessels in stages from the Atlantic entrance to the lake surface. Third, an identical lock system on the Pacific side would lower ships back to sea level. The entire route would use gravity alone. No pumps would lift the water. The lake sits higher than both oceans, so water flows downhill through the locks, then drains into the sea. The engineering economy was absolute. Every component either stored water, moved water, or contained water. Nothing else was necessary. Each lock chamber is a reinforced concrete box 1,000 feet long, 110 feet wide, and as deep as a 6-story building. The walls are thick enough to hold back the pressure of millions of gallons without flexing. When a ship enters from below, steel gates close behind it. Culverts open in the floor, and water rushes in from the higher chamber or the lake above. The ship does not rise because of any mechanical lift. It floats on the rising water. As the chamber fills, the vessel ascends with the surface until the water level matches the next stage. The forward gates open, and the ship moves into the next lock or proceeds into Gatun Lake. The ship is not pulled, pushed, or hoisted. It is simply allowed to float upward as the environment around it changes. The original design used paired locks, so two ships could transit simultaneously in opposite directions. Each chamber required the same volume of water, approximately 26 million gallons per lift. That water comes from Gatun Lake, fed by rainfall and the Chagres River. Every time a ship transits, 52 million gallons drain into the ocean and must be replaced by rain. The canal does not recycle the lockage water. The system depends entirely on a renewable supply from the tropical watershed. In an average year, rainfall is sufficient. In a dry year, the mathematics change, and so does the canal's capacity. By the time the canal opened in 1914, the lock design had been tested under steam power and with vessels displacing up to 65,000 tons. Ships entering the locks were guided by locomotives running on rails along the chamber walls. These locomotives, called mules, pulled cables attached to the vessel to prevent drift and collision with the concrete walls. The ship's engines remained in use, but the mules controlled lateral movement. The gates themselves weighed hundreds of tons, yet were balanced so precisely they could be moved by a single electric motor. The original machinery still operates more than a century later, evidence that the design solved not just an immediate problem, but a permanent one. Decades later, global shipping changed faster than the canal's dimensions. Container ships, bulk carriers, and tankers grew longer, wider, and heavier. The original locks could handle vessels up to 106 feet wide with drafts of 39.5 feet. Anything larger could not fit. By the late 20th century, shipbuilders designed two categories: Panamax vessels, built to maximum canal dimensions, and post-Panamax ships too large to pass. Trade routes, requiring a Pacific to Atlantic passage without using the canal, added thousands of miles and weeks of travel time. The constraint was not theoretical. It shaped the global fleet, the price of goods, and the routes taken by every container crossing the ocean. In 2007, Panama began construction of a third set of locks parallel to the original chambers. The new locks stretch 1,427 feet in length, 180 feet in width, and accommodate drafts up to 50 feet. These dimensions allow new Panamax vessels carrying over twice the cargo of the original Panamax class. The engineering principle remained identical: fill a chamber with water, let the ship rise, then open the gate. But the scale increased, and so did the cost. The expanded system uses water-saving basins that recycle roughly 60% of the lockage water, reducing the freshwater demand per transit. The original locks still operate alongside the new chambers, handling smaller vessels and maintaining canal capacity. The expanded canal began commercial operation on June 26, 2016. The project doubled the waterway's capacity and allowed larger ships to transit. But the addition did not resolve the underlying constraint. Gatun Lake still supplies water for both the original and expanded locks, and the lake depends on rain. During the dry season or extended droughts, water levels drop. When the reservoir falls below operational thresholds, the Canal Authority restricts the maximum draft allowed for transiting ships or reduces the number of daily transits. Lower draft means ships must carry less cargo to pass safely. Fewer transits mean delays and longer queues. The locks can lift any weight, but only if the lake holds enough water to fill them. In recent years, the canal has faced draft restrictions during severe dry periods, forcing operators to choose between limiting cargo loads and rerouting ships around South America. Climate variability has made rainfall less predictable. The Canal Authority has proposed additional reservoirs, but no new large-scale water sources have been completed. The system that solved an elevation problem in 1914 now confronts a supply problem with no clear engineering solution that avoids environmental and political trade-offs. Every proposed reservoir floods inhabited land. Every restriction on transits costs revenue. The canal operates under a constraint it cannot engineer away. The lock mechanism remains unchanged in principle. Water enters from above, lifts the ship, and drains into the ocean. Gravity moves 52 million gallons per transit with no pumps. The canal raises ships over a continent because engineers replaced the impossible task of carving down to sea level with the simpler task of lifting water and floating vessels upward. As long as rain refills the lake, the system works. When rain fails, the canal's capacity drops, and the global supply chain adjusts accordingly. The structure that conquered elevation now depends on weather it cannot control. The locks proved that impossible scale problems can be solved by changing the question. The lake proved that solved problems can create new constraints when the environment shifts. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.